Hello students, today we are going to study the design and drawing of a Sarda Type Fall. This design comes in the third module of Design of Hydraulic Structures from BTech Civil Engineering of APJ Abdul Kalam Technological University. This is the fourth design, that is design of Sarda Type Canal Fall. Now let us recall what a canal fall was. A canal fall is a solid masonry structure which is constructed on the canal if the natural ground slope is steeper than the designed channel bed slope. That is, a canal fall is provided for a transition from the natural ground slope, which is steeper, to the designed channel bed slope. Now, Sarda type canal fall is a classification of canal fall, and previously we have studied the trapezoidal notch canal fall. Now, this is the second one that we are going to design, that is the Sarda type canal fall or simple vertical drop fall. Now, the Sarda type canal fall consists of a single vertical drop over a crest wall, which allows the upstream water to fall with sudden impact on the downstream side. That is, this type of canal fall will be having a single vertical crest wall. That is, this crest wall means that is the wall constructed across the canal, and it can be having a trapezoidal cross section or a rectangular cross section. So, water will be simply falling over this crest wall. Now, this type of canal is constructed in Sarda Canal in Uttar Pradesh, and therefore it is named as Sarda Fall. That is, the name comes from the Sarda Canal as it is used in this particular canal, hence the name. And this type of canal is very economical and suitable for high discharges. And another speciality is that this type of canal is not flumed. That is, the width of the cross section where the canal fall comes, that is same as the initial width of the canal. That is, the width is not decreased to accommodate this canal fall. Now, this is an this is a graphic image of a Sarda type canal fall. We can see this is a trapezoidal crest wall. This is a trapezoidal crest wall, and it can be also given in rectangular shape. So, water will be, this is the upstream side, water will be flowing in this direction, and it falls over the crest wall to the downstream side. Here there will be a water cushion, same as in the case of a trapezoidal notch fall that we have studied earlier. So, this is a water cushion. As we can see, the floor is depressed here, and this is a downstream canal bed. So, water will be simply flowing over the crest wall and falling downwards to the downstream side. Now, let us come to the question. Here the question is to design a Sarda fall for a canal carrying a discharge of 40 cumecs with the following data. That is, upstream bed level is given as 105 meters, upstream full supply level 106.8 meters, downstream bed level 103.5 meters, downstream full supply level 105.3 meters. Now, bed width of the canal is given as 30 meters, and exit gradient is given as 1/5 or 1 in 5. Step 1, here we are going to find out the length and shape of the crest wall. As we have said earlier, the shape of the crest wall can be either rectangular if the discharge is less than 40 meter cube per second, and if the discharge is greater than 40 meter cube per second, we are going to select a trapezoidal crest wall, and the length of the crest wall will be equal to the bed width of the canal, as we have said earlier. Here fluming is not done, that is, the width of the canal is not decreased to accommodate the fall. Hence, length of the crest wall will be equal to the bed width of the canal, that is given as 30 meters. Now, upstream batter, that is, for the trapezoid, the upstream side slope is given as 1:3, and downstream batter, that is the downstream side slope, that is taken as 1:8. Now, here the discharge given in the question is 40 meter cube per second. Hence, we are going to design for a trapezoidal crest wall, since this 40 meter cube per second is greater than 14 meter cube per second. Hence, we are going to select a trapezoidal crest wall for the design. Now, step 2 is the calculation of canal drop, head loss and water depth. Now, in this figure we can see this is a trapezoidal crest wall with an upstream batter of 1:3 and downstream batter of 1:8 that we have discussed in the previous slide. Now, let us see, this is the upstream full supply level. This dotted line is the upstream full supply level, and from that at a height of V square by 2G, we have the upstream total energy line. Now this is this Y, that is a upstream water depth. Now this small d is a gap between top of the crest wall and upstream bed level. This is small d. Then we have small h, that is the gap between top of the crest wall and upstream FSL, that is small h. Now E is the gap between top of the crest wall and upstream total energy line. Now this is the actual drop height, that is the height difference between upstream bed level and downstream bed level. We can see if we extend this line up to here, this is the actual height of the drop. Now other terms are, we have small d, that is a gap between top of the crest wall and downstream bed level. Then we have dc, that is gap between downstream bed level and bottom of the water cushion. This is the value dc. Now there is lc, that is the length of the water cushion from toe of the crest wall to a point where the slope, this a point where the transition starts. So this is lc. So these are the important terms. And then there is downstream total energy line, downstream full supply line, full supply level, and downstream bed level. So Y is the water level itself and HL is a head loss. That is the difference between downstream total energy line and downstream FSL. That is a head loss that happened after the fall. Now some minor things, that is the upstream cutoff wall and downstream cutoff wall. We will be dealing with that later. Now in the second step, first we have to find out the canal drop. Canal drop is equal to level difference between upstream bed level and downstream bed level. These values are given in the question, so we will be getting it as 1.5 meters. Now next is head loss HL. This HL we have denoted in the previous figure, that is upstream FSL minus downstream FSL. That is equal to 106.8 and 105.3. We will be getting 1.5 meters as the head loss. These values all are given in the question. Now next is the water depth Y, that is equal to upstream FSL minus upstream bed level or downstream FSL minus downstream bed level. That you will be obtaining as 1.8 meters. And here we have said we are not going to do any flowing, that is the width of the channel section is not decreased to accommodate the crest wall. Hence the bed width of the canal will be equal to the length of the crest, that is equal to 30 meters. Step 3 is a calculation of small h and small d, that is from the previous figure. We have to calculate this small h and small d. And for a trapezoidal crest wall, the top width Vt is given by the equation 0.55 into root of h plus d. That is, you have to by heart this equation. And from this figure, you can see h plus d, that is small h plus small d is equal to y plus drop, that is this y plus drop. That is, from both are the level difference between this dotted line and this line, that is the downstream bed level. So that is h plus d is equal to y plus drop. Therefore h plus d is equal to 1.8 plus 1.5. These two values we have found out in the previous step. Therefore h plus d, it is small h plus small d is equal to 3.3 meters. Now substituting that value in the equation for top width of the crest wall, Bt is equal to 0.55 into root of 3.3, that is equal to 0.99, and we are approximating it as 1 meters. Now the discharge over the crest wall, we have an equation for the discharge, that is Q is equal to 1.99 L into h raised to 3 by 2 into h by Bt whole raised to 1 by 6. You have to by heart this equation also. So substituting the values, we have Q is equal to 40 meter cube per second. Then L, length of the crest wall, that is equal to the width of the canal, that is equal to 30 meters. Now h is the unknown, h raised to 3 by 2 into h raised to 1 by 6 by BT is equal to 1 raised to 1 by 6. Now solving this equation, you can get H is equal to 0.786 meters, and from that value you can find out small d. Therefore, we have obtained small h and small d. Now, height of the crest above the upstream bed, that is capital D. Height of the crest above the upstream bed, that is a level difference between top of the crest wall and upstream bed level, that is capital D is equal to y minus h, that is y minus small h, that is equal to 1.8 minus 0.786, that is equal to 1.014 meters. So in this step we have found out small h and small d. Step 4 is a determination of crest level. That is, we have to fix the level of the top of the crest wall. That is, we are going to find out the reduced level of this point or this line. Now for that, the reduced level at top of the crest is equal to upstream FSL minus small h, that is upstream FSL minus small h, that is equal to 106.8 minus 0.786 that we have found out in the previous step, that is equal to 106.014 meters. Now the canal side slope is not given, so we are going to assume it as 1:1. And next, velocity head is equal to v square by 2g. Now we have to find out the velocity head. For this, we have to find out the upstream velocity, that is v is equal to discharge by area. Discharge is given. Area is the area of cross section of the channel, that is trapezoidal in shape, and we have assumed the side slope as 1:1. That is 40 by L plus ny into y, where L is the bottom width of the trapezoidal channel section. Therefore, that is 30. That is then after substituting 40 by 30 plus 1 into 1.8, that is n is equal to 1, as the side slope is 1:1. Then do y, that is 1.8 whole multiplied by 1.8. Hence, velocity is obtained as 0.698 meter per second. Now, to find out the level of upstream total energy line, we have level of upstream total energy line is equal to upstream FSL plus v square by 2g, that is upstream FSL plus v square by 2g. So by substituting the values, we will get the upstream total energy line as 106.825 meters. Now we can find out capital E. See in this figure, capital E is the level difference between upstream total energy line and top of the crest wall, that is E is equal to upstream total energy line minus reduced level at top of the crest, that is equal to 106.825 minus 106.014, that is equal to 0.811 meters. Next, step 5, that is the design of cistern. Cistern is a portion where the water falls over the drop, that is water will be falling directly into the cistern, and that portion we will be having a water cushion, etc. So for the design of cistern, first we have HL we have found out, that is the head loss after the fall, that is 1.5 meters. Then minimum depth of cistern to be provided is DC, that is equal to 1/4 into E into HL whole raised to 2/3. You have to by heart this equation. Therefore, by substituting 1/4 into E, that is 0.811 we have found out in the previous step, and HL is equal to 1.5. So we get DC as 0.285 meters. Just approximate it as 0.3 meters. We will be providing a minimum depth of cistern as 0.3 meters. Next is length of cistern. We have another equation. L is equal to 5 into root of E into HL. By substituting, you get LC as 5.515 meters. So you will be providing, just approximate or round it off to 6 meters. Now the top level of cistern, that is equal to downstream bed level minus DC, that is equal to 103.5. Downstream bed level is given in the question. So 103.5 minus depth, that is 0.3. So the top level of cistern or top level of water cushion is equal to 103.2 meters. Here the top level of cistern means that is a floor of the cistern or floor of the water cushion. Okay, step 6, design of cutoff walls or curtain walls. First one, upstream cutoff. Here there are two curtain walls, that is at upstream side and downstream side. First we are going to design the upstream cutoff wall. Here the height of the cutoff wall should be at least 1/3 of the water depth. That is, depth of upstream cutoff is equal to 1 by 3 into y. Y is the water depth, that is 1.8. Therefore 1.8 by 3, that is equal to 0.6 meters. Now this is a minimum value, so we are going to increase the value slightly and choose 0.7 meters. Now provide a 0.7 meter deep cutoff wall with 0.4 meter thickness over a concrete layer of thickness 0.3 meter and width of 0.6 meter. That means this hatched portion is the cutoff wall which has a depth of 0.7 meter and a thickness of 0.4 meter. Now below that we have to provide a concrete layer which has a height of 0.3 meter and width of 0.6 meters. So finally the total depth of wall plus the concrete layer, that is equal to 1 meter, that is 0.7 plus 0.3, that is 1 meter. That means while we are designing the thickness of wall or finding out the pressures in the next steps from causeless theory, the total height of upstream pile will be 1 meter. We will be considering 1 meter as the total height of the upstream cutoff pile. Now next is downstream cutoff. Here also similarly the minimum depth of half of water depth should be provided, and therefore depth of upstream cutoff is equal to half of water depth, that is 0.5 into y, that is 0.5 into 1.8, that is equal to 0.9 meters. So we are going to increase that value 0.9 because it is a minimum value, so increase slightly to 1 meter. Now we are going to provide a concrete layer of 0.3 meter thickness and 0.6 meter width below this wall. Therefore total depth of wall plus concrete will be 1 plus 0.3, that is equal to 1.3 meters. In this figure, this hatched one is a cutoff wall, that is a downstream cutoff wall with a thickness of 0.4 meters and height of 1 meter. Now below that there is a concrete layer with a thickness of 0.3 meter and width 0.6. Therefore total height of downstream cutoff wall, that will be 1 plus 0.3, that is equal to 1.3 meters. Step 7, design of wing wall. There are two wing walls, that is on the upstream side and one on the downstream side. First one, design of upstream wing wall. Let r be the radius of the wing wall and r should be between 5 to 6 times the waterhead over the crest. That means the radius of the wing wall should be between 5h and 6h. Therefore 5h is 5 into 0.786, where 0.786 is the waterhead over the crest. Therefore 5h is 3.93 and 6h is 4.716. So choose a value in between this range. Therefore provide a radius of wing wall as 4.5 meters, subtending an angle of 60 degree at the center, and then carry tangentially for about 1 meter. In this step you have to remember that the radius will be between 5h and 6h, and everything else will be the same for every question. Therefore look in this small figure. This is a upstream wing wall with a radius of 4.5 meters and central angle, or the angle subtended at the center, that is 60 degree, and the thickness of the wing wall will be 0.4 meters. Okay, next is design of downstream wing wall. The downstream wing wall has to be kept straight to a distance of 6 into root of E into HL, where E is 0.811 and HL is head loss, that is equal to 1.5. These values we have found out earlier. Therefore that straight length of the downstream wing wall is equal to 6.618, and we are rounding it off to 6.62. After this length, the downstream wing wall is warped to a slope of 1:1 at a splay of 1:3 and is taken to the end. That this portion I will explain in the figure in the next slide. Next is height of top of downstream wing above the bed. That means water depth plus freeboard, and a freeboard of 0.5 meter is taken. Therefore height of top of downstream wing wall is equal to 2.3 meters. Next is length of warped wing wall, that is the length of the warped portion, that is x is equal to 3 into 2.3, that is 1 in 3, this 3 into 2.3 is the height. Therefore 3 into 2.3, that is equal to 6.9, and we are rounding it off to 7 meters. Now in this figure, as we can see, this is the upstream wing wall with the radius that we have defined in the step. These numerical values may be different, just see the figure here. Okay, now this is a upstream wing wall, that is a curved portion when we have defined the radius, and now this is a downstream wing wall. This is a splay of 1 in 3 as we have said earlier, and this portion is having a slope of 1 in 1. That means this height is 2.3 and the width of this portion, that is the triangular section, has a width of 2.3 at the base and height of 2.3. That is, the slope is 1 in 1. Now as we can see, we have said the splay of this portion of the downstream wing wall is 1 in 3. That means if the height is 2.3, this length will be 3 into 2.3, that is 6.9, and we have assumed this length as 7 meters. So this is the downstream wing wall and this is the upstream wing wall. So, and this is the trapezoidal crest of the the crest of the Sarda Fall. Now let's move on. Step 8, design of concrete floor. Here the design of concrete floor is done using the Koslow's theory. First we are going to do the floor length calculation. For that, the exit gradient GE, the equation of exit gradient, is given in the Koslow's curve or the Koslow's chart. So to do this problem you need the Koslow's chart. So in that we have this equation is given, GE is equal to h by d into 1 by pi root lambda, where h is a maximum seepage head, which in this question h is equal to RL of crust minus RL of downstream bed, that is equal to 106.014 minus 103.5, which is 2.514 meters, and d is the depth of cutoff at the downstream side. Now in the question the exit gradient is given as 1 by 5, therefore equating and substituting the values, that is 2.514 by 1.3, that is the downstream pile depth, that is equal to 1 into 1 by pi root lambda is equal to 1 by 5. Therefore 1 by pi root lambda is 0.013. Now from the chart, that is from the Koslow's chart of exit gradient, we can find out the value of alpha corresponding to this value, that is 0.103, that's the value of 1 by pi root lambda. Therefore alpha is equal to 17. Since alpha is equal to b by d2, b is equal to alpha into d2, that is b is the total length of the floor, that is equal to alpha into d2, that is the depth of downstream cutoff pipe. Therefore alpha is 17 into 1.3, that is equal to 22.1. That is a value, or that is the required length of the floor. So we are going to round it off to 22.5 meters. So we next provide 22.5 meter of total floor length. Now minimum floor length required on the downstream side, that is equal to 2 into y plus 1.2 plus HL. So by heart this equation, 2 into y plus 1.2 plus HL, where y is the water depth and HL is head loss. That is 1.8 is the water depth and HL is 1.5. So substituting you will get the value of 7.5 meters. That is a length of 7.5 meters should be provided on the downstream side beyond the toe of the crust wall. So this is a minimum length of floor required on the downstream side. So we are going to take a higher value than 7.5, that is we are going to provide 10 meter length on the downstream side, and the balance length of 22.5 minus 10, that is equal to 12.5 on underside of the crust wall and on the upstream of the crust. Here the usage of Koslow's curve for exit gradient is shown here. As we can see here, there are curves between alpha versus lambda and alpha versus 1 by pi root lambda. We are using this curve and using this equation, that is exit gradient G is equal to h by d into 1 by pi root lambda. We have found out the value of 1 by pi root lambda, and that value is 0.103, and using this value we can find out the value of alpha from this curve corresponding to this value, that is 17. That is 17 is the value of alpha corresponding to 1 by pi root lambda is equal to 0.103. That is, in this figure we can see this is the downstream side of the flow, that is from A to E. So that is, we have provided that as 10 meters, and balance will be on the upstream side and below the crest wall, that is 12.5. Now next, estimation of floor thickness by Koestler's theory. Now we have to design the thickness of the floor on different points. So here we are going to assume the thickness of floor at the start and the end, that is in the upstream side and downstream side as 0.4 meters. We are going to give the minimum thickness on upstream end and downstream end, that is 0.4 meters. Next we have to find out the thickness at points A, B and C. Here A is a point at the toe of the crest wall, then B is a point 3 meter from the crest, that is from the toe of the crest, and C is a point 3 meters from B. So we have to find out the thickness at A, B and C. Now we are going to calculate the pressures at points A, B and C using Koestler's theory. Now at upstream cutoff, we have a pile at the upstream side. So at upstream cutoff, the depth of the pile D1 is equal to 1 meter. This value we have defined earlier. Then B is the length of the floor, that is 22.5. That is also from the previous steps. Now this is the upstream cutoff pile condition. We have to find out the pressures at E1, C1 and D1. So we have 1 by alpha is equal to D1 by B, that's equal to 0.044. By using Koestler's chart, we have phi D is equal to 12% and phi E is equal to 18%. Therefore, to find out phi C1, we have to take 100 minus these values, that is 100 minus phi E, that is equal to 100 minus 18, that is equal to 82%, and phi D1 is equal to 100 minus phi D, that is equal to 88%. Now, next we have to apply. Now we have found out the pressures at C1 and D1, and phi E1 is 100%. Now, as the piles are at a far distance, that is greater than 2D, the effect of mutual interference of piles is small and is neglected. That is, we don't have to do the correction for mutual interference, we have to do the corrections for thickness only. Here, the usage of Koestler's chart for finding out the pressures is shown. For the upstream pile condition, we have to find out C1 and D1. For that, first we have to find out 1 by alpha, that is equal to D by B, that is depth of pile divided by this length, that is B. We got 1 by alpha as 0.044. From that, for this value of 1 by alpha, we have to take the values of phi D, that is from this line, and phi E, that is from this line. So phi D value, that is from this curve, is equal to phi D is equal to 12 at this point, and from the phi E curve, this value is 18%. Now, to find out the correction for thickness, I have taught you the way by using similar triangles. That is, at upstream end, the thickness of floor is assumed as 0.4 meters. Now, phi C1 is 82, phi D1 is 88. Look in this figure. We have this phi C1 is 82, phi D1 is 88. We have to find out the pressure value at thickness of 0.4 meters. So that is, we have to find this value, that is phi C dash. For that, this x by, consider this small triangle and this larger triangle. We have x by this value, that is phi D1 minus phi C1, that is x by phi D1 minus phi C1 is equal to, in this triangle, this height, that is 0.4 divided by this height of the larger triangle, that is 1, that is equal to 0.4 by 1. From this you get x is equal to 2.4, that is x equal to 2.4. Therefore phi C dash, that is phi C1 dash, is equal to phi C1 plus x, that is equal to 84.4 meters. 84.4%. Now at downstream cutoff, this is a condition. We have to find out the pressure values at E2, C2 and D2, and the downstream cutoff pile depth is 1.3 meters, that is equal to D2. Now we have 1 by alpha, that is equal to D2 by B, that is equal to 1.3 by 22.5, that is equal to 0.057. Now from Koslow's chart, we have phi d2 is equal to 14% and phi e2 is equal to 24%. Now at downstream end, the flow thickness is assumed as 0.4 meters. We have assumed this value earlier. Hence, correction for thickness. Next, we are going to find out the correction for thickness for phi e2 using the same method as we have done in the previous, that is for the upstream cutoff condition. Here we draw a triangle like this, that is a trapezoidal like this, and phi e2, this is phi e2, that is equal to 24, and phi d2, that is equal to 14. Now we have to find out the value here, that is phi e2 dash at a depth of, or at a considering a thickness of 0.4 meter at the downstream end. That is using the same method, x by phi e2 minus phi d2 is equal to this value, this height, that is 1.3 minus 0.4 divided by this whole height, that is 1.3. Therefore x is equal to 6.92 and phi e2 dash is equal to phi d2 plus x, that is equal to 14 plus 6.92, that is equal to 20.92%. In this slide, the usage of Koslow's chart to find out the pressures for the downstream pile is shown. We have to find out the value of phi e and phi d. For that, first we have to find out the value of 1 by alpha, that is equal to d by b, where d is the depth of the downstream pile, this is small d, and b is the length of the floor. So we got alpha as 0.057, and corresponding to this value, we have to find out the value of phi d and phi e from the curve. This is a phi d curve, and this is a phi e curve. So corresponding to 0.057, the phi d value is 14%, that is this blue line, and phi e value is 24%, that is this green line. Now we have found out the pressures at this point, this point, this point, and this point. Next, we have to find out the pressures at points A, B, and C. For that, we are assuming that the pressure varies linearly from 84.4% to 20.92 along the total length of the flow. That is, from this point to this point, the pressure varies linearly from 84.4 to 20.92. That is, we are representing that in this figure. That is that linear variation from 84.4 to 20.92. So we can see this is a variation or linear variation shown as a straight line. Now we have to find out the pressure set A, B, and C. For that, we are using this figure, and as we found out the the correction for thickness, we are using the same method here. By using similar triangles, we have to find out PA, PB, and PC, that is percentage pressures at point A, B, and C. Now for that, we are taking this height as small a, so small b, and this is small c. Length up to A, that is 12.5, total length is 22.5. Then distance between A and B is 3 meters, B and C is also 3 meters, and C to the end, that is 4 meters. Now we have to find out the pressures at A, B, and C. At A, using similar triangles, we have this small a. We are considering this triangle, that is triangle with a base A, and a larger triangle, this triangle. Okay, now small a by 84.4 minus 20.92, that is this gap, that is equal to, this is the height of this triangle, or the, not the height here, it is a base of this triangle, that is 10 divided by total length is 22.5. From that we can get A is equal to 28.21. Therefore pressure at A, that is equal to PA is equal to 49.13, that is 20.92 plus A. Using a similar technique, you can find out small b and small c and PB and PC. Hence at B it is B by 84.4 minus 20.92, that is equal to 7, this length, that is 4 plus 3, 7 by whole length 22.5. Therefore you get small b, and PB is equal to 40.67, and similarly PC is equal to 32.20. Now using the value of head remaining at or pressure remaining at A, B, and C, we can find out the thickness of the floor required. That is, at the upstream end and downstream end, we have assumed a floor thickness of 0.4. Now at point A, Percentage pressure PA is equal to 49.13. This is not here, this is capital PA. Capital PA is 49.13. To find out the thickness at point A, we need the static head. That is, static head at A is equal to residual head at A plus depth of water acquisition DC. That is, static head at A is denoted as HA, small HA, is equal to residual head at A is small PA. That is, small PA plus depth of water acquisition, that is DC. So that is, the static head is HA is equal to PA, that is small PA plus DC. Now residual head at A, that is head remaining at A, is equal to PA, that is percentage, this is a percentage pressure, that is 49.13 divided by 100 into H, that is equal to small PB. Now capital H is a seepage head, that is equal to RL of the crest minus RL of downstream bed, that is 2.514, that is 49.13% of this value remains at point A. That is 49.13 by 100 into 2.514 is the residual head at A, which is denoted by small p. Now small PA is equal to 49.13 by 100 into 2.514, that is equal to 1.235. Now static head at A is equal to 1.235 plus 0.3, that is small HA is equal to small PA plus DC. This is small PA, DC is the depth of water acquisition, so static head at A is 1.535. Hence thickness TA is equal to HA by G minus 1. From that you can get the thickness required at A as 1.1 meters. Now provide 1.1 meter thick cement concrete flooring overlaid by 0.2 meter thick brick pitching for a length of 3 meters. That is, from A to B we have to provide 1.1 meter thickness and 0.2 meter thick brick pitching above the cement concrete flooring. Now similarly at point B we have static head HB is equal to small PB plus DC, where small HB is equal to 40.67, that is a pressure, percentage pressure at B, 40.67 by 100 into 2.514, that is at B 40.67% of 2.514 remains. Therefore residual head is 40.67% of 2.514. Therefore HB is equal to 40.67 into 2.514 divided by 100 plus 0.3, that is 1.32. Now this 0.3 is the depth of water acquisition. Next is thickness at T, that is TB is equal to 1.32 by 2.4 minus 1, that is approximately 1 meter. Here also we are going to provide 1 meter thick concrete floor overlaid by a brick pitching of 0.2 meter for a length of 3 meters, that is from B to C. Now next at point C also the same method. We have small hc is equal to small pc plus dc, where hc is equal to 32.2, that is the percentage pressure at point C, and 32.2% of 2.514 plus 0.3, that is approximately 1.109. Therefore TC is approximately 0.8. Here also similarly we have to provide 0.8 meter thick cement concrete floor overlaid by 0.2 meter thick brick pitching for a length of 4 meter length of the floor, that is from C to the end, that is 4 meters. Next is the same step 8, design of concrete floor using Bligh's theory. For the exam you can use either Khoslas theory or Bligh's theory, or use the method specified in the question. Here maximum seepage head H is equal to RL of crest minus RL of downstream bed, that is equal to 2.514, we have found out in the previous step. Now in Bligh's theory we use the creep length, hence total creep length L is equal to C into H, where C is the Bligh's coefficient that will be given in the question, or else you can assume the value of C as 8. So total creep length L is equal to 20.112. Now vertical creep is equal to 2 into D1 plus D2, that is the D1 and D2 are the depth of upstream pile and downstream pile, hence vertical creep is 4.6 meters. Now length of impervious floor, that is equal to total creep length minus the vertical creep, that is equal to 15.512. So assume it as 16 meters. Now minimum length of downstream flow, that is the same equation we used earlier. So its value is 7.5, approximated as 8 meters. So downstream floor, that is from the toe of the crust wall to the downstream end, that is 8 meters. So length of upstream floor, that is equal to 16 minus 8, that is equal to 8 meters. Hence provide 8 meters from the beginning of the floor to the toe of the crust. Now next is we are going to design the thickness of impervious floor. We have total creep length L is equal to 2 into d1 plus L plus 2d2. This L is the value of length of floor that we defined in the previous slide. Hence total creep length L is equal to 2d1 plus L plus d2. Substituting the values, you will get it as 20.6 meters. Now provide a minimum thickness of 0.4 meter at the upstream end and downstream end. Now this is a figure. Here this hatched portion is the crest wall. As we can see, this is a upstream pile and this is a downstream pile. Now as in Koslow's theory, we are going to find out the thickness at the toe of the crust wall, then at a point 3 meter from the toe, and that is point B. Next at a point C, that is 3 meters from point B. Now thickness at point A, that is the toe of the crust wall. Using Bligh's theory, head lost up to A, that is equal to H by L into L1, that is a creep length up to A. That is H is a seepage head, L is the total length of the floor. Now creep length up to A, that is L1 is equal to 2d1 plus length of floor up to A, that is 10 meters. Hence head lost up to A is equal to 2.514 by 20.6 into 10, that is equal to 1.22 meters. Hence that is head lost up to point A. Hence residual head at point A, that is the remaining head at point A, is equal to total head minus head lost up to point A, that is equal to 1.294 meters. Now thickness at A is equal to, using the equation from Bligh theory, that is TA is equal to HA by G minus 1, where HA is a static head and G is the specific gravity of concrete. We have HA, the static head, that is equal to residual head at A plus depth of water cushion, that is 1.294 plus 0.3, that is equal to 1.594 meters. Hence thickness TA is equal to 1.138 and round it off to 1.2 meters. Now provide a 1.2 meter thick cement concrete flooring overlaid by 0.2 meter thick brick pitching for a length of 3 meters, that is from A to B. Now thickness at point B, that is 3 meters from the toe of the crust. We have creep length up to B, that is equal to 2 into d1 plus creep plus length of floor up to B, that is 2 into 1 plus 11, that is equal to 13 meters. Now head lost up to B is equal to 2.514, that is a seepage head available, 2.514 by length of floor into 13. This 2.514 by length of floor is the hydraulic gradient, that is H by L into 13, that is the creep length up to point B. Hence head lost is 1.586 meters. Now residual head, that is head remaining, is equal to total seepage head minus head lost, that is equal to 0.927 meters. Next is static head at B, that is equal to residual head plus depth of water cushion, that is equal to 1.227 meters. Now thickness at B is equal to, using the same equation, T by G minus 1, sorry, HB by G minus 1, that is 1.227 by 2.4 minus 1, that is approximately 0.9 meters. Hence provide a 0.9 meter thick concrete flooring with brick pitching over it for a length of 3 meters, and the brick pitching will be having a thickness of 0.2 meters, same as in the case of thickness at point A. Now thickness at C, using the same method as we used for thickness at A and B. Now point C is 3 meters from B. Now creep length up to B is 2 into d1 plus 14, that is the length of floor up to B, sorry, up to C. So 2 into 1 plus 14, that is equal to 16 meters. Now head lost up to C is equal to hydraulic gradient, that is 2.514 by 20.6, that is H by L into creep length, that is equal to 1.953 meters. Now static head at C is equal to residual head plus depth of water cushion, that is equal to 2.514 minus 1.953 plus 0.3, that is equal to 0.861 meters. Now TC, that is the thickness of floor required at C, that is equal to 0.861 by G minus 1, that is 2.4 minus 1, that is equal to 0.615, approximated as 0.7 meters. Now provide a cement concrete flooring of 0.7 meters overlaid by a brick pitching of 0.2 meters for 2 meters, that is the remaining length of the floor from C. Next is step 9, the design of protection works. First is upstream protection. On the upstream side, we are going to give a brick pitching like this, and the depth of this brick pitching, that is equal to the water depth, that is 1.8 meters, that is this depth will be 1.8 meters, and is laid on the upstream side towards the crest at a slope of 1 in 10. It is given like this, and this slope is 1 in 10, and a 20 centimeter drain is provided from this point for draining the water on the upstream side at the time of maintenance or any other works. Next is downstream protection. For that, the length of bed pitching is equal to 9 plus 2 into HL, where HL is 1.5, that is length of bed pitching is 12 meters, and this may be provided horizontal up to the end of the masonry wings, that is masonry wings is a downstream wing wall, and then provided at a sloping of 1 in 10, that is up to the masonry wings it is horizontal and then it is sloping, that is the length of the horizontal pitching, that is a horizontal length of the pitching will be equal to the length of the warped wing, that is equal to 7 meters. We have found out this value earlier. Now the remaining length of the slope pitching is equal to 12 minus 7, that is 5 meters. That is for 7 meters the downstream protection will be horizontal, and remaining 5 meters it will be sloping at a slope of 1 in 10. Next is slope or side pitching, that is a side protection given for the sloping sides, and it consists of 0.2 meter thick brick pitching on the edge, and this has been warped to a slope of 1.5:1, and side pitching is supported on a toe wall of 0.4 meter thick and 1 meter deep. Next is energy dissipators. It consists of 2 rows of friction block in cistern and 2 rows of cube blocks fixed at the downstream end of the impervious floor. Now these cube blocks are also known as chute blocks. Now we are going to design the size of this friction block. For that, we have critical depth YC is equal to Q square by G raised to 1 by 3. This you have studied in the open channel flow or at the time of hydraulic jump studies. YC is a critical depth, that is Q square by G raised to 1 by 3, where Q is the discharge per unit width. Here width is 30 and discharge is 40, therefore Q is equal to 1.33, and hence YC is equal to 0.565, approximately 0.6 meters. Now length of one block is taken as 2 into YC, that is equal to 1.2, and width and height of block is taken as YC, that is equal to 0.6. Hence it will be a cube having a length of 1.2 and height and width of 0.6. Now distance from top of crust is taken as 1.5 into YC, that is equal to 0.9, and approximated as 1 meters. Next is size of cube blocks. Length equal to width equal to height is equal to 1 by 10th of Y. That is Y is a water depth, that is 1.8 by 10, that is equal to 0.18. Approximated as 0.2 meters. Now that concludes the numerical part of the design. Now we are moving on to the drawing of Sarda Type Fall. We have completed the numerical design of Sarda Type Fall. Now we are going to prepare the drawings based on the numerical design that we have already done. We have to prepare a half foundation plan, a longitudinal section and a lateral section. Now this is a complete sketch of the drawings that we have to prepare. Now note that the values given in this figure are not according to the numerical design that we have done. You have to draw this figure using the design or the values that we have obtained in our question. The values in this figure are not according to our design. This sketch is of some other design, but the figure is the same itself. Now look here. The top one is the longitudinal section. This is a half foundation plan. That means on the half of the figure shows the actual plan, and that is the top half shows the actual plan and bottom half shows the plan at the foundation level. Then there is a lateral section. See, this is a lateral section, and that section is along this line A, B, C. So that is a lateral section. Now let us see in the longitudinal section. We can see here, this is the upstream or top of the upstream wing wall. This line is the upstream FSL. This is the crest wall of the Sarda Type Fall. Then this is the downstream bed level. Then there is, see, this is a bed pitching on the upstream side, and this line has a slope of 1 in 10. Now this channel, see, this is a drain pipe used to drain the water from the upstream to the downstream if needed. Then these are the friction blocks, that is to dissipate the energy of the fall. That is, due to this fall there are chances of formation of hydraulic jump, so we have to dissipate that energy. So for that these friction blocks are used. Then this is a downstream wing wall, and as we can see here, this line is stepped. That means this is actual steps are provided here for the transition from upstream wing wall to downstream wing wall. As we know that there is a vertical fall here, so on the wing wall there will be a stepped portion. Then this portion, this depressed floor, this is a cistern or the water cushion that has a depth of 0.3 meters in according to our design. Now this is the floor of the Sarda Type Fall. This is the upstream cutoff wall. This is the downstream cutoff wall. Then these are the different depths of or different thickness of floor that we have designed. See, at A, that is a toe of the crust. Here this was our point A. Then here after 3 meters comes our point B. Then this is point C. So at these points A, B, C, we know that the thickness is different. So that thickness should be shown here, here and here. Then these are cube blocks that also we have designed in our numerical design. That is also for dissipating energy. Then from here the wings are warped. That is, the purpose of that is that, as we know, the original channel section is trapezoidal, but at the section of the crest wall or at the section of the Sarda Type Fall, the section is actually rectangular. That means the bed width of the trapezoid, that width is provided at the section of the Sarda Type Fall or the crest wall, and at that section the channel section is rectangular with the width as equal to the bed width of the trapezoid. So as we know, there is a transition from trapezoidal section to rectangular section. Then after that this portion will be also having a rectangular section. Then from this point, that rectangular section is gradually transformed into trapezoidal section for the remaining portion of the canal. So before the channel or before the Sarda Type Fall, the channel is transformed from trapezoid to rectangular, and after the fall it is again transformed from rectangular to trapezoidal. So this is that portion where this warped wings, that means there the transition takes place. Then after that there is this portion here, bed pitching is provided here, then side pitching is provided on the sides of the trapezoid. Then here a slope of 1 in 10 is provided, and this is a toe wall. And after that from here onwards the actual downstream bed width is prevailing here. Now when we come to the plan or half foundation plan, as we know, above this line we have the actual plan or the top view, and below this line we have plan at the foundation level. So at the foundation level, this is a upstream cutoff wall and this is a wing wall. So this is the foundation of the wing wall. As we can see, this is the foundation of the wing wall. This is the foundation of the crest wall. Then these are the, this is a toe wall, and here we have the upstream cutoff wall, downstream cutoff wall. Downstream cutoff wall is here. This is a downstream cutoff wall. Then in the actual plan we have, this is a crest wall of top width 1 meter. Then these are the friction blocks and they should be staggered. That means the friction blocks should be oriented in such a way that they are not parallel, they should be staggered. Then here we have the cube blocks. Then this is a upstream wing wall. As we know, we have designed the radius of this wall. Then this is a downstream wing wall with a splay of 1:3. Then we have, this is a warped wings where we know the transition from rectangular to trapezoidal section takes place. Here we have side pitching on the sides of the trapezoid. Then this is a toe wall, and here from here onwards actual bed level or the downstream bed level prevails here. So from here to here, that is a fall structure. Then this is a section on ABC, that is ABC. Sometimes for the university exam you will be asked to draw a section at the center line of the crest wall. So in that case what happens, it will be symmetric and not like this. As we can see here, for this much portion we have a section of this much, and for BC we have this section. So if you are going to draw a section here, this thing will be on the both sides, that is at this portion the section is rectangular only. So we can see here, this is as we can say this portion is the abutment of the crest wall, and it can be provided stepped or it can be provided as a trapezoid, just like an embankment. So these dimensions are not needed because we haven't designed for the dimensions of this abutment wall. This is a bed pitching. Then at this portion we have the cistern. See here, this AB line lies where the cistern is there. So this is FSL and this is the top of the downstream wing wall. As we can see, this level will be equal to the top of this line. This is a downstream wing wall. Then this is a toe wall, and this is a sides of the trapezoid here. As we can see, that is a portion where this transition takes place. There also we have brick pitching. So this much is what you have to draw for the question, and you have to show importance should be given to the dimensions defined in the question, and also the reduced levels of different portions. So keep that in mind. So we will see the actual hand drawn figure. This is an actual hand drawn figure. See, these are the important things to be noted. Sometimes some levels or dimensions may be missing from this figure that you can add according to the design. So this is a half foundation plan and cross section on ABC, and this is a longitudinal section. As we can see, this concrete layer is not shown in the sketch that I have shown before, as we have designed for this rectangular concrete layer that has a thickness of 0.6 and a height of 0.3, and here also there is a concrete layer that acts as a footing below the cut-off walls. So that concludes our design and drawing.